committee and everybody who helped to prepare the conference here, and also Sumya, who was my personal guide here on my very first trip to India. Okay, now to my talk. I'm coming from Germany, so before speaking about science, I quickly want to introduce myself, or the city where I come from. I'm from Leipzig. There are some pictures in the top row of this slide. You can see demonstrations started, and the Eastern Communist Bloc collapses afterwards. Leipzig is also known as the city of music and the city of science. So this guy here, this is Johann Sebastian Bach, a very famous classical musician who worked in Leipzig for 60 years. There are other philosophers here as well. For instance, this is Nietzsche, famous German philosopher. And because I'm an engineer, I have to put some engineers here on this slide as well. So this man here is the founder of the NASA, North American Space Agency, who was born in Leipzig in the 1930s. And finally, this man here on the right is Professor Pabel. He has won the Nobel Prize for Medicine 2 years ago. So everybody was very proud that we have had the Nobel Prize in town. So my university, HTWK Leipzig, is rather young. So it was founded in 1992 after Germany got reunified. But the university is some kind of agglomerate of many universities under one roof. And so the history goes back very long until 1764. Our university nowadays is a technical university with some core profiles, and engineering composite materials is one of them. Personally, so I'm a professor for composites. My background is strongly in textile composites, and that's why I also like, really, it's a pleasure for me to be here. I've done a lot of research in composite modeling. I will slightly show about parts of that here in my presentation too. But I also work in diagnostics and in multifunctional materials and in the design of complex materials, textile composites being one of them. I have two research groups. So one research group is the so-called Composite Circularity Lab, CCL, which mainly deals with topics of circularity, recycling, sustainability. I'll show some examples of the research later in my talk. And a second research group, the Advanced Materials and Structures Lab, which focuses on multifunctional composites, on nanocomposites, on additive manufacturing, but also on advanced models for composite design. So, enough talk about me. My presentation is divided into three major parts, but before coming to this, I want to a little bit introduce into the problem. We have heard about this in the morning session as well. There was a lot of talking already by Professor Petru or of Olga about sustainability. So as you know, or as you may know, the ambition of the European Union is to become the first continent who becomes climate neutral. And there's a lot of political effort also towards that direction, the Green Deal, and also the so-called twin transition. So twin transition means green transition and digital transition, or twin transition. But as we are engineers or material scientists, the question comes up, so what can we do to support that goal? And there has been, let's say, a think tank established by the European Union. This think tank is called the Advanced Materials Initiative 2030, and they have written a so-called Materials Manifesto. And here you can see some, let's say, buzzwords of topics that should support the green transition. And as you can see, the topics are very wide. So we have the classical lightweight materials here, maybe, but also carbon capture, or recycled materials, etc. And I just marked with those red boxes here what I will tackle in my talk today. So as you can see, my talk will be pretty wide. And I also want to mention this little green box down here. So circularity being like a cross-sectional topic that covers all of the topics mentioned before. So this think tank has written a roadmap with action fields. Translated into science speech, that directly means that is where the money goes in the next 10 years. And you see that I marked it bold. Materials with tailored properties is one very important topic, but also renewable materials, recyclable materials, and bio-based materials. So very much overlap to the topics you have been discussed about before. But what is also very important is digital technologies, product traceability, and life cycle management. Yeah, and so that gives some kind of umbrella to the topics I'm going to show in my presentation. So the first major part of my talk will be multifunctional composite materials. So I'm going to speak about two things. First, structural batteries, and second, nano-composites. So I will start with structural batteries. So first question comes up when you hear this phrase, structural batteries. What is this? What is a structural battery? Or the door of your car could be the battery. And you don't need a battery anymore, or at least smaller batteries. So there's a liquid electrolyte and a separator to avoid short circuit. And everything is packed into a pouch bag made of aluminium or of copper. And now the idea with carbon nanotubes, as you can see on this picture here. That is what we have done with a French company called Nava. And the idea in both cases is to increase the surface of the material to get a higher surface, specific surface, structural batteries. So at the moment it's everything manual. So we first produce the parts of the carbon fiber of the battery. And then this is all assembled into a pouch cell and cured. And in the end you have something like this that looks pretty much like a normal battery. You see some pictures of the test in the left. And we also developed models for predicting the properties of those materials. And here in this picture you see a comparison of experiment versus simulation. It fits pretty well. So the result of that study is like this. So we have investigated, there is a certain area of multifunctionality. This is here, this triangle. And you have to reach that triangle to make the multifunctional material work. And so what we have done is we investigated many potential material combinations. increase of performance compared to the current approaches in literature with a unidirectional anode and a woven cathode. So that is actually what we have right now. Then we have combined this with a second material, so-called carbon nanotube fibers. So everybody has heard of carbon nanotubes already, and you can also produce fibers out of that. And those fibers are very flexible. They are even so flexible you can make a knot into the fiber and it does not crack. So this is kind of spectacular. Those materials are suitable. We have produced a drone. So this is a micro drone. So the size is here. It's very small. Fits on your hand. You can put it on your hand. It looks like this. We have produced the material by additive manufacturing, so 3D printing. We investigated the microstructure, did numerical simulation to prove that such a structure holds the load, and also investigated recycling issues. That's the question that comes up very often in that context. And the end looks like this. So this is like a mini drone. There's a little video here. So we made it fly for a couple of seconds. So without any battery. There's no battery inside that drone. So the material itself is the battery, like I showed. So still there's a lot to improve there, but we proved that this technology is able to work out. The second example that I'm going to show, I've picked this particularly for the Indian audience here, is nanomaterials. So it's very well known that you can use nanocomposites for sensing purposes. Due to time issues, I'm not going to explain all the scientific details. I'm coming to the application immediately. So what we have done is we produced a nanocomposite containing of carbon nanomaterials. So in this case, again, carbon nanotubes. We mixed the carbon nanotubes with classical polymers, and we 3D printed those devices here with standard 3D printers. So this is not rocket science, so normal printers. And the idea is to use that as a sensor for detection of water pollution. So usually, if you want to prove that water is polluted, so you can use samples, send the samples to a lab. It's very expensive labs, and they do a lot of fancy tests, and then you get a result. But our approach was to provide a cheap, immediate solution for, let's say, on-site detection. So there was a mobile test device. So here's a little hole. You put those sensors into the hole, and what we have shown with our analysis is that the nanomaterials strongly increase the signals. That means if you have, let's say, a tiny bit of pollution, pesticides or something like this, you can even detect small amounts of pollution immediately with a pretty... So you may know that implants, like if you have implants for your head or for your knee or whatever, that you can produce those materials with composites, also with 3D printing. And there the important question is, you have to have a material where human cells can grow into. So your body cells must be able to grow into that implant, to have a good connection between the implant and your real body. And so we've seen that in the morning already with lattice structures. So important is here the geometry. So different geometries, but also to provide conditions for the human cells to grow into. And there, nanomaterials or nanocomposites can help as well. So you've seen this drone already. It was the little object flying for a couple of seconds. And I'm doing a lot of work in modeling. And when you want to model those multifunctional materials, you have a lot of dirty multi-physics problems. A lot of people say composites are difficult, which is true, and also a challenge of us as researchers. But those multifunctional materials are even more difficult, because you have electrochemical problems. I'm not a chemist, I don't understand that stuff. Well, she smiles here in the first row. You also have thermocoupling, so batteries, you know that from airplanes, yeah? Batteries get hot. So there are always those stickers. If your mobile phone gets hot, inform the crew or something. And there's a lot of safety issues connected with that problem that usually come up when I present those materials. And important here is, first of all, to understand what's going on. And in that context, modeling is very helpful. So we did a lot of effort here. We published a couple of papers about that topic in the last 2 years. And I've chosen a second example because this is textile composites. I also wanted to show something for classical textiles. When you think of automotive engineering, you use technical textiles for automotive engineering. We have heard that before. So usually if you take a textile and you drape that textile into a complex geometry like this, the textile will not look like regular, like planned, but there are certain effects, draping effects, some call it draping errors, that have to be considered. And so we did a lot of work together with KIT, so Karlsruhe Institute of Technology in Germany, to model those effects with the coupling of diagnostics, computer tomography diagnostics, and also simulation diagnostic analysis. And now that brings me to the third and final part of my talk, sustainability and circularity. Here I have again two examples to show. And the first one is circularity of large-scale composites. So we have seen already this morning that we can produce large-scale composites for many applications, wind energy blades, airplanes, etc. Especially wind energy has seen a big growth in Europe, but the thing is, such a wind turbine only has a lifetime of 25 years. And afterwards, it looks like this. It's waste. And we as composite engineers, we claim this is a high-performance material. We should not treat that as waste. I always say, I don't take the gold, my golden ring and put it to landfill. Yeah, this is expensive stuff. We should not throw it away. And so there's a lot of conversation about circularity, and the approaches there is to use that material again. So we have created a strategy that we call R6 strategy. So when a material is produced in operation and reaches end of life, that we can reuse that material for something else. And so what I investigated was repurposing, so the reuse of a material for other purposes. And I'm going to show an example about this. So what we have done is we investigated floating PV systems, so swimming solar cells, which is very interesting for countries with less space. So there are parts in Asia, Singapore, Hong Kong, where there's no space, but also in Europe. And so a lot of people put solar cells on the water. This has many advantages. I don't want to go into detail here, but usually those swimming solar cells, they are placed on regular plastic elements, which are throwaway pieces, more or less, but they also create a lot of waste, which can be avoided. So solar cell, put it onto a rotor blade, and then we've upscaled this to a larger element with 4 solar cells. So this here is 5 meters times 2 meters. We did a lot of simulation. We produced those elements, and we also tested this in a water test, and that looks like this. So we created some waves, and to prove that that those elements also can be used when there's a lot of waves on the sea, etc., etc. Okay, and the final example is of my talks coming from the construction sector. There's a lot of talk in Europe that the construction sector has a large problem with CO2 emissions, especially concrete structures. So old structures look like this: thick houses. You need electricity to feed them. You have a lot of thermal losses and a lot of energy consumption. And the idea, which is also like in Europe kind of a law already, is to provide zero emission buildings, which don't need any additional energy. You can create them probably by solar cells. And especially in a sunny country like India, you could argue, okay, you could create so much energy that you have more energy than you need, and then you can feed electric cars by this. So that is the idea. And the question now is, how can you do this? You have to have lightweight materials. Oh, he's showing a clock. I have to stop talking. Give me 2 more minutes. You need lightweight materials with high insulation properties. And for that purpose, we used carbon concrete. So concrete reinforced with carbon fibers, and we produced sandwiches with aerogels as a sandwich core. It looks like this here. So a material which has a very low lambda value, so very good thermal properties. And we are able to produce this material in automated production. So I'm going to skip the manufacturing due to time issues. We also tested those materials in bending experiments and show that the properties are very, very good. So that brings me to the summary of my talk. So I hope that
May I now invite Professor Rajesh Kumar Mishra from Czech University of Life Sciences. Sir, please.
मैं हूँ राजेश मिश्रा, भारतीय हूँ जन्म से और मेरे चिंतन से, लेकिन क्योंकि इंटरनेशनल कॉन्फ्रेंस है मैं अंग्रेजी में बात करूँगा। सो माननीय भारत सरकार के वस्त्र मंत्री श्री गिरिराज सिंह जी, प्रोफेसर बेहरा डायरेक्टर TIT भिवानी, श्री मल्होत्रा जी डायरेक्टर NTTM, श्री सांगरी जी डायरेक्टर PhD हाउस PhD चैम्बर ऑफ कॉमर्स, my colleagues from Europe, Japan, and most importantly, dear student friends. So, today I will talk about bio-based polymer composites with fibrous reinforcement for several applications, mainly in automotive and construction industry. Currently, I work at the Department of Material Science and Manufacturing Technology in Czech University of Life Sciences, Prague, in Czech Republic. So today we signed 2 very important MOUs. We have Professor Alice Kosoret, who is current and source of abundance for all scientific growth. I need to go back a little bit to Prime Minister Sri Lal Bahadur Shastri ji. He said Jai Jawan, Jai Kisan, and now we added Jai Vigyan. Therefore, it's held the soldiers, held the farmers and scientists. These three are important pillars for self-reliance, security, prosperity and growth, not just for any country but for the whole world, for human civilization. So today I will try to justify how our scientific activities in textiles are connected to these three professional groups and to humanity as a whole. Because we are talking about India's potential, a little bit information about where India stands in the world with respect to availability or production of natural fibers. And I will deal with waste materials. India is probably one of the biggest, if China and India to be compared or not, doesn't matter, but India is growing with its potential of natural fiber and its availability. At the same time, we are also producing huge amount of waste. Waste for other industries, but it is the raw material for us as material scientists. So we try to prepare value-added, high-value products out of waste material. Today I will touch upon a few ideas how waste materials can be converted into high-value products, and that is where comes the importance of polymer-based composite materials. As we know, cotton, hemp, sisal, bamboo fiber, fiber from pineapple waste, from coconut waste, everything from waste. We have a lot of natural fiber. Mainly when they are derived from plants, they are rich in cellulose. And cellulose is a highly crystalline ingredient which is helpful for strengthening of materials like composites. At the same time, we have abundance of protein-based fibers from silk, for example. The best quality fiber is excellent for thermal insulation, for decorative textiles, but there is also a lot of waste in the process. And we are now exploring possibilities how to produce high-value composites from such waste fibers. We cannot leave any single fiber to be wasted. It is now different era. Now little bit information how is India's outlook. There is some information on the internet, and India is one of the largest, in fact it is the largest producer of cotton and jute fiber. And there is a big thrust to further improve production of silk and jute, etc. in future. There are many schemes coming up by the government of India, especially from the Ministry of Textiles, about cotton productivity, natural fiber scheme, silk scheme. So these are many initiatives these days being taken up, how to improve the production, application and potential of natural origin fibers in multidisciplinary applications. And composites are one of emerging areas where we can utilize. Since I am a material scientist, I focus on agro waste. My university at present is focused on agricultural products. Fibers are natural fibers, also are agro products. Wool from sheep is agro product. Silk also is agro product. But not to forget several other waste materials from agricultural process. For example, the rice husk, the cover of a rice grain. It's a cattle feed, or sometimes people just burn it to prepare some carbon. Or it's not a high energy producing fuel, but we will try to use it in reinforcement of composites. Not that we are the first one to think like that. Our ancestors have been using rice husk together with mud to make cottages. And why did they try to do it? Not because they had a plenty of this husk, but because they understood very quickly that this husk is filled with air, stagnant air. They didn't have thermal insulation measurement equations, they didn't in a better way, but not that it is the first time. Banana plant, for example, produces a lot of waste, and we extract fibers known as banana fiber. I will talk a little bit about sugarcane fiber, fiber from agro waste from corn, and some other things, and how they can be utilized. The philosophy is based on sustainability and minimization of waste. So many people talk about 5 hours, 7 hours, like reducing utilization of resources, That means very precisely using things in productive manner. Reuse, wherever it is possible to reuse waste products, and recycling, as Honorable Minister also pointed out, from waste. We talk about biomass because product from agriculture is definitely for food, for clothes, for everything. But there is a lot of waste which is left for degradation in the natural environment. We call it biomass. Biomass, for example, rice husk, coconut waste, banana waste, pineapple leaf, etc. We are trying to utilize such biomass to make composite products. Composite, I think definition is not required because already you understand there is a reinforcement, there is a matrix, and in this case we are using fiber material as a reinforcement. Because fibers, which are core to textile engineering, are very special form of mainly polymers because of the high orientation of polymer chains along the axis. And this scientifically too much about this cellulose and ingredients of plant products, but we must keep in mind cellulose is key to reinforcement in composites. We already know for centuries that lot of fibers exist in nature, starting from cotton to jute, some fibers from fruits, some fibers from leaves, some fibers from stem, and now we will explore possibilities to extract fibers from other lesser known parts of the plant. Little bit world statistics, there is a huge global composite industry prediction and it's increasing day by day. Why? Because energy is depleting. We cannot rely on petroleum for too long. Therefore, latest research in Europe and developed parts of the world is about electric vehicles, hydrogen as a fuel, and non-conventional energy sources, for example, wind energy, solar energy. So, future is about using non-petroleum based products and renewable unconventional power sources. India's potential trend also is very positive trend predicted for the next 5 years and maybe next few decades. Whatever we do, we are attached to nature. We are part of nature. And nature is source of all scientific innovations. If we understand things around us, we are able to produce things, reproduce things. In fact, if we learn from nature, we will be excellent scientists. So composites are naturally occurring in human body. For example, we are reinforced, our stature, our strength, build up is because of the bone, skeleton. And skeleton is surrounded with muscles and tissues to give it a composite structure. Fruits, for example, imagine a fruit without a seed. If there will be some fruit and no seed, will that fruit have that definite shape? Probably not. Definitely not. Because the handloom is world famous, silk woven saris and things like that, silk kimono from Japan. But this process, we know how the silk is produced. The cocoon has a moth, and if it makes a hole and flies as a butterfly, it's their life. But we lose our business making high quality silk filament, laminated composite products. In this case, many of my colleagues spoke about making sandwich composites. We make layers of natural fiber, layers of synthetic fiber, glass fiber, with jute, with flax, woven fabrics, non-woven fabrics, and make a comprehensive three-dimensional robust composite. Little bit focus to cellulose. This rice husk, as such, in the raw form, can be added to concrete, can be added to cement, to enhance the thermal insulation performance and mechanical stability. Some people also do kind of producing carbon from this husk and add it to concrete. We know about 3D printing or modern additive technology. So this type of concrete reinforced with husk is used for 3D printing of building materials. Maybe you are aware that the whole building can be 3D printed, not just brick by brick and being plastered. The conventional process takes 6 months, 1 year, 10 years. But this process is much faster. For example, an auditorium like this can be 3D printed in 1 week time. And it will be still robust, strong, because it is a step-by-step, layer by layer. I think many of youngsters are researching on 3D printing of composites and other high-performance materials. So there are examples of how this natural filler reinforced concrete can be 3D printed and making constructions. India, like many other countries who have big oceans, have plenty of coconut. Coconut is a nice fruit, but there is a lot of waste fiber, coconut husk, coconut fiber. We prepare carpets, ropes, they are existing. Still there is a waste. Any textile process produces a lot of waste. Also as consumers, we produce a lot of used clothes annually. We are trying to find ways to recycle and reuse such consumer waste, agricultural waste and textile industry waste. In which processes do we produce a lot of waste in textile process? For example, in cotton, carding, in foaming, there is a lot of short fiber, and conventionally that is used for making pillows or something, or as an oil being discarded. So now our goal is to identify such waste materials. For example, hard waste in weaving also can be made into secondary yarns. We are using it in the automotive, for example. It needs to absorb the sound, noise, and these fibers are very good candidate because they have these channels of air which can absorb the sound. Corn is produced in India and everywhere in the world, and except the crop, there is a lot of fibrous waste from the leaves, from the cob, and it's possible to extract these fibers for reinforcement. You know this process, squeezing sugar cane to produce juice and sugar afterwards. But this bagasse or the waste of sugar cane also is highly fibrous material. It's not just good for composting or burning. We are able to extract fibers, not for wearing, but definitely for reinforcement into composites by impregnation with some suitable resin. There are examples where such materials are combined with other synthetic fibers. Why synthetic fibers? Still, we are in a hybrid stage. Why? Synthetic fibers are definitely stronger because we know how to create stronger fibers. Nature produces fibers not perfectly oriented, not perfectly crystalline, but they are degradable, sustainable. Therefore, we try to adopt natural materials and combine them with high performance fibers, maybe high performance waste fibers, and this hybrid material is definitely solution in this stage because they are partly degradable, partly high performance. 3D printing or additive manufacturing is very good technique because it involves high precision. At the same time, the raw material can be based on natural fillers. I talked about hybridization, therefore sometimes recycled plastic bottles are combined with biomass, especially from agricultural waste, to produce composites. Currently, our research is focused on hybrid composites, combining natural fibers, natural waste, and waste of synthetics. What are applications of such composites? For lightweight yet robust transportation systems, furniture, sports items, also automotive components. I will show something later. Another very high value fiber waste is from palm fiber. I will skip these things, but I will mention definitely what are the potential candidates of fibers waste for making composites. Here are examples of automotive applications, buildings, in electrical insulation, because they are insulators of electricity, for ships and things like that. We can make construction materials, for example, artificial wood from wood particles for housing, and concrete which is porous. This is especially important in snowy countries or when there is high rain. So this concrete can drain the water down, and also these channels are very good for thermal insulation. Alright, we have an abundance of bast fibers from other agricultural crops. We can make composites, and I want to just tell that some of these natural fiber based composites are no less than synthetic fiber based composites. Therefore, flax, for example, is excellent to replace glass or carbon in certain cases, not everywhere. Bicycles are made from composites. Some porous plants like the banana stem and wetland plant, they are also porous for making composites with sound insulation performance. Sound insulation is important in today's context. A lot of vehicles and noise being produced. Alright, waste of wool. There are many advantages of natural fiber based composites, but there are also some critical issues to be taken care of. We have to make a compromise. Alright, what building? Here is a special construction material made from bamboo and glass. So it's possible. Bamboo sometimes can be misleading, because bamboo fiber is not produced directly from plant but by a chemical process like solvent spinning, we know. So this is otherwise natural bamboo. We make construction materials to make houses. Basalt is high value fiber from nature, also from volcanoes. We combine basalt with jute, basalt with natural fibers to have high value composites. Coconut shell, for example, we use it for making particles of micron and nano size to be used in fillers. Professor Robert and others spoke about nano composites. So we use natural fillers from agro waste in composites. We make hybrid composites. Here is example of a spacer composite from, you can see, jute fiber, polyester and resin epoxy. These spacers are very good for small kiosks in airports, containers, trucks, like that. And you can see samples. These are based on natural fiber and synthetic hybridization. They have excellent sound absorption. We do little bit of modeling as well. Compressional resilience is excellent because these spacers can act like springs. They can absorb the impact and recover. For example, you can think of applications in military and other fields. So I want to thank everyone for your kind attention. And
going forward, may I now request our alumnus and President Textile Association India, Sri R.K. Vidji, to please present the vote of thanks.
हमारे माननीय टेक्सटाइल मिनिस्टर गिरिराज जी, जो बहुत ही सिंपल हैं, प्यार करते हैं, सिंपल भाषा में बोलते हैं, आज हमारे बीच में हैं। जब भी हम पिछले 1.5-2 साल से इनसे मिलते हैं, एकदम इनसे एनर्जी आ जाती है। हम हमेशा फाइबर की बात करते हैं, मैनमेड फाइबर की, कॉटन की, विस्कस की फाइबर की बात करते हैं, परंतु ये फर्स्ट टाइम है जो बजट में, फर्स्ट टाइम बजट में उन्होंने कहा है नेचुरल फाइबर, मैनमेड फाइबर एंड न्यू एज फाइबर, जो आज मिश्रा जी ने बताया न्यू एज फाइबर के बारे। दिस इज द फ्यूचर, जो आज से हम 100-150 साल पहले यूज करते थे, वही इन्होंने एक प्रथा चालू की है और यही फ्यूचर है, यही फ्यूचर है। वो कितना हमारी एनवायरनमेंट कितना गंदा होता जा रहा है, सॉइल खराब होती जा रही मैनमेड फाइबर से। हमारे बैरा साहब, प्रिंसिपल साहब, मैं जैसे ही एंटर किया, मैंने मेरे 1969 को मुझे दिन याद आ गया जब मेरे फादर यहाँ मुझे भर्ती कराने ले आए थे। पहले ज़माने में तो भर्ती कराते थे, दाखिला नहीं करते थे। तो जब माखड़िया जी के पास आए तो उन्होंने कहा कि इनको टेक्सटाइल में भर्ती करना है। तो उन्होंने कहा, वैसे ही पूछते हैं किसका बेटा है, ये आपका ही बेटा है। तो मुझे तब पता लगा कि मेरे पिताजी ये हैं या ये हैं। तो पुराने ज़माने में कितने सिंपल लोग होते थे। तो मैं जब अंदर आया तो कॉलेज का मैंने देखा, मुझे वो दिन आज से 56 साल पहले याद आ गए और मेरा इतना मन बाग बाग कर गया। तो आते ही मैंने लैब में, जैसे मैं गाड़ी खड़ी की तो मैंने पूछा गार्ड से, कैसा है कॉलेज, कैसा है? उसने कहा, जब से बैरा साहब आए हैं कॉलेज चेंज होता जा रहा है, कॉलेज बहुत अच्छा होता जा रहा है। तब 240 स्टूडेंट थे जब हम होते थे, 60 स्टूडेंट हर साल निकलते थे। आज 1800 स्टूडेंट्स हैं। मैं सबको, अपने बिरला जी को बधाई देता हूं कि उन्होंने इतना बड़ा इंस्टीट्यूट बनाया है। थर्ड, अशोक मल्होत्रा जी, जो इसी कॉलेज से ही हैं, उन्होंने जब से NTTM में ये काम शुरू किया है, टेक्निकल टेक्सटाइल बढ़ता जा रहा है, बढ़ता जा रहा है और यही फ्यूचर है। तो मैं टेक्सटाइल मिनिस्ट्री को पूरा धन्यवाद करता हूं, क्योंकि आज हमें मौका मिला है। मैं कभी कभी अपना गिरिराज जी से जब देखता हूं ना इनको, तो मेरे मन में ये आता है, तुम हो तो गाता है दिल, तुम हो तो गाता है दिल, तुम हो तो मेरी जिंदगी, तुम हो तो रास्ते भी हैं, तुम हो नहीं तो रास्ता भी नहीं है। और ये मैं आपको बता देता हूँ, मैं टेक्सटाइल से तो अटैच रहा हूँ, हमारे सीनियर भी बैठे हैं, जूनियर भी बैठे हैं, इंटरनेशनल आदमी भी, प्रोफेसर्स भी बैठे हैं। जो पिछले 1.5-2 साल में हमारे ऑनरेबल प्राइम मिनिस्टर जी ने जो काम किए हैं, गिरिराज जी ने काम किए हैं, SQC क्वालिटी कंट्रोल, हर लेवल पे पूरी वैल्यू चेन पे, फाइबर टू गारमेंट अपैरल, सबको रॉ मटेरियल एट इंटरनेशनल प्राइसेस पे मिले, उन्होंने किया। जीएसटी जो हम इतने सालों से कह रहे थे इन्वर्शन जीएसटी है, उन्होंने इन्वर्शन खत्म किया, 5% जीएसटी कर दिया। कोई उसमें नहीं है जितने में कपड़ा खरीदो उतने में गारमेंट बनाओ। तो और ये जीएसटी का ईज ऑफ डूइंग बिजनेस किया। पीएलआई स्कीम लेके आए, जैसे गिरिराज जी आए, इन्होंने इमीडिएटली जब हमने कहा कि छोटे छोटे एमएसएमईज के लिए भी लाए जाए, तो उन्होंने छोटी सी 50 करोड़ की पीएलआई स्कीम लेके आए। तो मैं तो ये कहता हूँ, लास्ट में सबका धन्यवाद करता हूँ। कहते हैं कोशिश करने वालों की कभी हार नहीं होती, सफलता एक चुनौती है, स्वीकार करो। जब तक सफल नहीं होते चैन से बैठो मत, संघर्ष छोड़कर मैदान से भागो मत, बिना कुछ किए जय जयकार नहीं होती, कोशिश करने वालों की कभी हार नहीं होती। धन्यवाद।
यहाँ उपस्थित सभी गणमान्य देवियों और सज्जनों, मैं आप सबको मध्याह्न भोज के लिए आमंत्रित करता हूँ।
फटाफट गाड़ी में दे महज एक नृत्य करने वाला
वो गया है जी?
नहीं, मैं फिर बोला था।
अच्छा,
दोबारा।
ओ वाह वाह।
और मेरा मन खुश कर दिया। वो लगभग 50 करोड़ पे
हाँ जी हाँ जी हाँ।
चला गया।
हम बताओ, टेक्सटाइल का जीरो नहीं जानता था, वही आपका
नहीं, आप तो जानते थे। दे देंगे
उसमें उसने सर्दियों के लिए जो अभी पिछले साल आपसे मिला होगा।
ये बाउल दे दो ना भाई सब्जी के लिए। एक लड़का छोड़ के बाकी सबको निकालना चाहिए, सबको नहीं बोले आप।
मैं आपसे पूछूं,
कब क्या करना पड़ेगा?
अभी उसके लिए बहुत काम करना है। गाड़ी के लिए जितना पावर चाहिए तो उस वेट से उतना पावर नहीं आ रहा। ड्रोन के लिए बहुत कम पावर चाहिए क्योंकि ड्रोन की वेट बहुत कम है, इसलिए वो ड्रोन में ही अभी चल जाता है। गाड़ी के लिए अभी नहीं पावर चल
हार्दिक कैसा विवाह है
किस चीज का?
अगली बार आना तो आएंगे। ठीक है सर। अमित
आपको बहुत बहुत
technology, viewing technology. This topic is specific. Last two presentations were
मिश्रा जी ने
very
बहुत
good.
अच्छा मिश्रा ने
वो दोनों presentations ठीक.
नहीं, बड़ी हिम्मत का काम है। बहुत अच्छा किया। जिस हालत में नहीं अच्छा है, बहुत बढ़िया। ठीक है, अच्छा लग रहा है। चल
Sure, sir. Bye, sir.
Around 2018. So it was built in 2008 under the second generation IT. It was started in some polytechnic college, and now we have shifted to our permanent campus. So you may, whenever you get chance, please do visit. And happy Science Day to everybody. Today is a great day for all of us. So just go to the application, like the Kevlar, as we all know that it is used in goods. So if you look at across the application horizon, it is basically subjected to mechanical loads which are varying in nature in terms of amplitude or intensity. It is subjected to thermal, electrical load, impact loads, humidity, corrosive environment in naval applications. Now all these basically leads to different kinds of damages into the system. One of the primary damage in composite that we all know is delamination, which is like the breaking between the plies, or debonding, which is the failure of the bond between the matrix and the fiber, matrix cracking and fiber failure. Now, when we want to ensure the safety of the operations or during service condition, it is very important to basically we are able to quantify and assess this damage. Where is the damage, how wide or the size of damage, and how it is going to affect the service life of the component. So these are very important questions that we need to ask, and we are trying ways to basically address this question through intervention of the nanotechnology in the composite design in itself. So like what is the challenge here? Like unlike metals, there are like lot of good techniques available like radiography or CT scan, where we can basically detect the damage during the quality control or the industry scale. But composites are completely different ball game altogether. Why? Because they are inhomogeneous, they are anisotropic, and that creates a lot of problems. So whenever you are second problem is that many times like the delamination is not on the surface, it is in the bulk of the system. So from the outside you don't see. You see that it is perfectly fine, but inside the damage is growing without even you knowing it. And then it leads to catastrophic failure, because when the damage is sufficiently large, you cannot prevent it anymore. Then multiple mode exists, right? Like I told in the previous slide, that there is debonding, delamination, and fiber cracking. So all these basically makes it difficult to detect the damage correctly. And but of course, when there is a problem, of course, it makes the problem more interesting, and that's why we are working on it. So what are we looking for? We are looking for an efficient approach to accurately detect different types of damages induced in the composites or the component or the structure itself. Now there are already many health monitoring approaches which we use in the structure as of now. Like for example, we have ultrasonic based method, acoustic emission based method, embedded sensor based SHM, vibration based and optical method. Now the question is, why can't we use all this? What is the point of like developing something more, right? So the problem with these approaches is that, for example, if you are using ultrasonic waves, the wave speed, suppose you have a fiber and a matrix, now wave speed will be different in two different systems. Now once you get the signal, change in the signal, you have to relate it to the damage. Now because there are multiple materials present inside the system, you don't know whether the change in signal is because of the interface or because of the real damage. That's a big question these people are asking. Same thing if you are using acoustic based technique, right? So what is the optimum amplitude to send to the material or the structure so that I can capture the damage? So these are like some of the limitations, that these materials are not that efficient in detecting the damage in composite as compared to their efficiency in the metals, right? Then if you are using embedded sensors, basically you are creating more interfaces into the system. The more interfaces, they basically act as a crack nucleating sites, and the crack starts propagating there, because materials don't like any interfaces, right? Okay. Then other thing is the size of the environmental damage. So when suppose you are having wind turbine, let's say they are exposed to a lot of varying atmospheric conditions, so there will be a scatter, like a big breadth of the size of the damage. Some damage may be in mm, some damage may be in micron. So what kind of technique you are going to follow? So those are the questions that basically help us or motivated us to go for alternative technique. Another big problem with these technique is that you have to ground the structure. For example, your aircraft is flying and you want to go for inspection. You cannot do it on the fly. You have to ground the aircraft, you have to ground the component or the structure. So that means it cannot be used during the time of it is being inspected. So the question is that how can we accurately monitor all these kind of damages, and is it possible to do the same thing on the fly, that means without really grounding the structure, right? So that will save a lot of time in terms of inspection and the cost that is associated with the inspection. So what exactly we are looking for? An efficient strategy that can sense the damage while the component is really used. So if you look at the analogy, our human nervous system, right? So whenever we have a cut, we always get a sensor. Sensor sends a signal that you feel pain, and pain is the signal here, and that pain tells you that you also know where is the cut, right, and how big the cut is. Without really looking at it, you can see like different ways of realizing the pain. So what we want to create is that some kind of a smart composite which has its own nervous system, so that whenever there is a damage or some discontinuity into the system, we can sense it through some way, right? So that is the idea that we wanted to move forward. Now, once we are okay with the idea, the next question that we need to ask is, can I scale it or for industrial use? Because it cannot remain, if it is only in the lab, then it is useless. So that is another question that we are looking for. And another thing is that on the fly use for naval and aero applications, because that is a huge cost associated with grounding the system. So we don't want that. Right. So what we, it's a like old, not really new concept. The problem is that nobody has used it for like insulating materials like Kevlar or glass fiber composite, right? So what we are trying to hear is that whenever there is a damage, that means there is a discontinuity in the system. Discontinuity will lead to the local increase in the resistance of the material. And because of, if we can monitor that change in resistance as a function of the damage and map it to the size of the damage, we know where is the damage and how big the damage is, right? So that is what we are trying to create here. Now the problem with the Kevlar is that it's a very high resistance material. So it is very difficult to accurately monitor the change in resistance, because the resistance is order of 10 power 6. So when something is mega ohms or even higher, if there is a change of 10 ohm, you can't detect it. It is almost negligibly small. So first we need to work out basically in terms of the resistance. So we need to improve the conductivity of the Kevlar or decrease the electrical resistance of the Kevlar. So basically now you have, on the other hand, you have a CNT, right, which is very highly electrically conducting material. It has a very good electrical properties, optical properties, and almost all properties are good, right? So we can create a sensor network within the Kevlar composite using CNTs, and then we can do all the mapping or the voltage measurement, and then do the conductivity mapping or what kinds of all sorts of things that we can do to basically map the change in the resistance to the size of the damage, location of the damage, and all other parameters which are associated with the damage, right? Okay. So basically this is what we were trying to create. Now the question is that how do we add CNTs, because there are many approaches. So the two approaches which we looked at is like you can graft the CNTs on the fiber surface. Like in one of the slides, Professor Bond was saying that you are having this porous electrode. So basically you can also coat the fiber with the CNTs inside the CVD reactor. But the problem is that the size of the sample is limited by the size of the reactor. So you cannot really create a big sample. It is as big as your size of the reactor, which is like CVD is mostly used technique. So that we basically didn't prefer in this. Now another thing is that can we modify the matrix by dispersing the CNT into it, because matrix is everywhere in the composite. So that means that my nervous system will be everywhere in the composite. It is basically accessed by all the possible positions, right? Okay. So this is easier. Of course, it is easy to scale also, because you just have to use the modified reagent, that's all, in your existing manufacturing setup. So you don't need to make any wholesale change in the production line of the composite. So that's in terms of attractive for the industrial people, right? Now the catch here is that we need to determine the optimum concentration. How much CNT to be used? What is the right amount of CNT? Because if you are doing too much, there are other consequences. For example, the viscosity of the resin will be too high. You cannot process the composite using all the composite processing techniques, right? So those things, challenges will come. So that's what we determined using electrical percolation analysis. Of course, there is a lot of theoretical framework that I am not going too much into it. But after doing some theoretical calculation, we basically came up with the concentration of about 0.58%, and then we verified it with the experiment. So then we dispersed the CNTs into epoxy using these probe sonication. Here are the parameters, and then they are nicely dispersed across the whole volume of the CNT. And then we compared the properties. So this is the DC conductivity and this is the viscosity. So DC conductivity basically it's the typical power law behavior. Here it is basically when there is a percolating network of the CNTs within the epoxy, there is a sudden jump in the electrical conductivity of the order of 10⁹, which means, and beyond that if you go, then it is almost flat. That means the conductivity is not changing. So there is no point of adding more CNTs beyond that point, because we are unnecessarily clouding plus making the system more viscous. As you can see here, that viscosity up to this point is more or less comparable, but the moment you go above, the viscosity basically increases quite a lot. And that has a very detrimental effect on the composite properties, because the wetting of the fabric will not be proper when your resin is more viscous. So you don't have a good bonding between the fiber and the matrix, or you have a poor debonding strength, right? So all these questions, so basically from this analysis we came up with the 0.58% is a okay choice to basically modify the conventional press system. Okay, so let's just skip it. There is a resin system, so certainly we have used, and then this presentation is used. Chairman, so you can take. So then we use basically our compression bonding setup, and this is the conventional system, and this is the modified system where you can see the CNT network inside it. And then we did the electrical analysis. So you can see here there is a huge jump in the electrical conductivity is improved by the order of 6. So 10⁻10 Simon per meter is the conventional electrical conductivity of conventional Kevlar composite, and it goes to 10⁻4. So it's a quite big jump in terms of electrical conductivity, which means the resistance of the composite has come down significantly. Now we can basically monitor the change in resistance through our measurements. Okay. Then we did also some more analysis in terms of debonding strength, what is the interfacial shear strength, and we basically made the setup here. Maybe I don't know, I can just show you directly. So this is a very common test that we use. Okay, let's do it. And then we tested almost all kinds of properties with respect to the mechanical properties of composite. So for example, internal shear strength, there's a 36% increase, and then mode 1, mode 2 fracture toughness, that also improves quite a lot. Like mode 1 is more 60%, and mode 2 is about 30%. And then basically we looked at the fractography analysis, done some more FEM calculations, to come up with a mechanism that basically leads to this kind of enhancement in terms of mechanical property. So if you look at the conventional system, the crack is growing at the interface, a little bit in the epoxy region. But if you look at the modified system, then there is a lot of zigzagging of the crack, and that requires a lot more energy, and which eventually leads to higher toughness of this modified system, right? So we have good evidence to support this mechanism. So you can do the fractography analysis, look at the more carefully pictures, like you see a lot of matrix cracking, and these are CNTs pull out here, so they take extra energy from the system, and same thing we observed in the mode 2 as well. So all these mechanisms lead to higher toughness or higher mechanical properties. Okay, then we looked at the damage sensing, right? So we have done two tests on, like, this is under mode 1 and this is under mode 2. You look at, this is quite interesting. So what we have plotted here is the change in resistance as a normalized by the base resistance, and this is the percentage. So as you basically apply the load or apply the displacement, the load is increasing, and then resistance initially there is not significant change, but then it actually builds up, right? So this is basically where the damage basically coalesces or damage evolves. Now at this point there is a sudden jump in the resistance, which is basically marks the propagation of the crack inside the sample, which means there is a sudden failure in the system, right? And same thing basically happens in mode 2 analysis. So this gives us a way to monitor the size of the crack inside the system, right? Okay. This is one of the objectives that we want to see. The second question that we wanted to ask is, I mean, how can we use this in terms of like other materials, right? So for that, first we need to understand how the variation of delta R with respect to delta I. Delta I is the size of the damage here, and then we can fit a power law type equation here, where K and N becomes the material parameter, and for Kevlar it is about 2.2 and N is this. But then the question is that is this applicable only for Kevlar? Then I mean power law, you can fit anything with the power law right now, right? So then we tested some other composition of the same thing, layered materials, right? So you look here, like we have carbon fiber, glass fiber, and fiber metal laminates, these are glare panels. So we have tested the same thing in all these layered systems, and we found that Kevlar law basically, power law predicts the change in the evolution of the resistance in quite well in all kinds of layered materials, with of course different K and N. So basically we can use this kind of relationship to predict what kind of delta R you expect in the system, and then we can go for an unknown system and see, and then try to correlate, and that we have all validated all these things. Again, we used a similar kind of technique to detect the delamination in the bulk system. We put these bucky paper sheets, which is basically sheets of CNTs between the laminas, and then we verified the same thing here. And you can see here that if you put at different layers, you can basically monitor the progressive damage in the composite, because each signal comes after a certain time. So we can see how the damage grows inside the system. So just conclude the takeaway here, that CNT dispersion allows you to monitor the change, basically monitor damage in the system. It also helps in improving the mechanical properties, right? Okay, now we are looking to scale it up to use in some real application. I just quickly want to just show this. So now the next step that we are trying to make a basically textile which is more smart, just like our chameleon. You can look at the change in the color. So what we are trying to integrate this with our damage sensing mechanism. So together we will have a very advanced system in terms of technical textiles which are used in the defense application mostly. Right? Yeah, of course. Thank you for your attention. And yeah, maybe you can get more ideas from talking with you.
Thank you very much.
Economical.
They might be more economical, but they will lack in the accuracy.
Okay.
So it depends on how accurately you want to measure the damage.
Okay. But for concrete, you are...
Concrete, it will work. It works. We have seen now.
Okay. I'll be in touch.
Thank you for your interaction. And since we are running sort of...
Bye.
So our next speaker is Dr. Prasad from Road Research Institute, Government of India. Dr. Prasad. Please, Dr. P.S.
Yeah, good afternoon to everyone. And thanks to the organizers and Professor G. V. Ramana for giving this opportunity, for delivering this lecture. And I am the do's and don'ts. So many, what is the advantage? If you won't use the properly, then what will be the final output? And this is our institute. It's a 75 years old Central Road Research Institute, New Delhi. It is very near to Nehru Place. And we are doing a lot of work on the applications of geosynthetics in the road infrastructure. We have a very good lab related to geotechnical testing. So, yeah, why geosynthetics are required? As a basically in the geotechnical applications, we will use for the ground improvement and at the same time to save many natural resources. So where we will use, basically it's an expansive place, collapsible soil and peat, marine clay. Wherever the ground is very soft, there we will use this geosynthetics. And what are the applications? Geosynthetics will be applicable in the area of geotechnical engineering, geo-environmental, transportation, hydraulic. Why? Because we will get a very good quality, whatever the strength we will get within the time. So these are the, just I won't go deeper, these are the types of geosynthetics we will use in the geotechnical application, geotextile, geomembrane, geogrid, and clay liner, geocells, geocomposites, like that. So these are the geotextiles. You know very well the geotextiles are woven and non-woven. And geogrids, basically we will use for the uniaxial geogrids, we will use for the flyovers, and the biaxial geogrids we will be useful for the improving the bearing capacity. And these also the geogrids, uniaxial and biaxial geogrids. So these geogrids we will use for the flyover, and this biaxial especially we will use for improving the bearing capacities. And geonets, geomembranes, especially, and the geocells, wherever the subgrade CBR is very poor, this will, geocells will give the confinement for the material. So geocomposites, especially for the drainage purposes we are using, and these are the geocomposite matrices for the erosion control. Geofoam, this is a very good material where the subgrade is very poor and it won't take much load on the soil. We can use the geofoam and see the density will be very low, so people can be used, but we are not using much because the non-availability. Otherwise the quantity is good here. If someone says, then we can use in fields. The field is ready already. Okay. And basically in the geosynthetics, geotechnical area, where we are using as a reinforcement, as a separation, filtration, drainage, fluid barriers and products. These are the basic functions we are using for the geotechnical applications. And these are the each material has its own function. So this is the table where we can use the geotextiles. Earlier we will use as a reinforcement, but nowadays we are not using much because it may puncture the things. Geogrid we are using as a reinforcement, and geofoam especially for only as a reinforcement, and geocomposites we are using like a drainage purposes. So this is the one of the best example is the soil is very poor and it won't take so much load. Like you can see in many villages and even in many highways also you will see this one. So in such areas what we are doing is we are using the geogrid or geocells or a combination of both at the subgrade level, so that what will happen, your modulus of improvement factor, especially for the block cotton soil. The block cotton soil, the CBR will be very low. The CBR is nothing but California bearing ratio, and if it comes to landslide material or thermal block, the modulus improvement factor is low then. So the basic thing is that if you want to use the geocell, just blindly we cannot use. So wherever the bearing capacity is low, means subgrade is low, CBR is low, there only we have to use. So then only the advantage will get. Otherwise if you use here, you won't get much advantage in that one. See, this is the way your base course thickness, this is the pavement layer thickness, your base course thickness, if modulus improvement factor is 1, 250 and it comes to remaining thicknesses are same, here it is 125. So what we can do is, we can reduce the base course thickness approximately up to 14 to 50% if we improve the use of the geocells. So this is the pavement layer thickness. If you conventional normal pavement thickness, if you use the geocells, the pavement thickness can be reduced. So around we can reduce the 35% of the DBM layer. So it is actually DBM layer is a very costly affair. So if you can save 35%, it is a good saving of the material. Similarly, even geocells you can use like a reinforced wall also. This is in Bhutan, they can in the BRO compound they use it for a car parking. So you can use like this also. This is one of the application of the geocells. And this is a very common problem in the highways. You will see many gully erosions along the embankments. So you can see the deeper also. So if you want to prevent that one, we can use the geocells along the slopes. I can show you the here. So like this along the slopes you can use and fill up with the concrete so that you can avoid the cracks on the embankment slope and it will prevent for the erosion. Similarly, you can use the natural geotextiles, jute or coir geotextiles. This is the coir geotextile. Even with the coir they can make the geocell fabric also. So these are some of the applications we can use for the land hill slopes also to prevent the erosion of the soil, and even we can use for the embankments also. You can see here along the roadside slopes we can use. But the most important thing is there you have to anchor properly at the top. Otherwise it will slip and the purpose won't get the things. So this is the way you can lay, and at the same time proper overlapping is also required. Otherwise what will happen if the gap is like this, then again the gully erosion will start. So this is one of the highway embankment slopes with the jute geotextile or coir geotextile, and finally after getting the grass, the slope will be prevented against the erosion. Even you can use at the subgrade level also natural geotextile so that it will improve the CBR, and after once it will improve the CBR, this will be naturally decompose the material. So these are some of the applications by using the natural geotextiles also. If it comes to the reinforced soil walls, so these are the block fascia. Everyone sees this type of flyovers, or this is the concrete fascia and gabion fascia. These are the flyovers, reinforced soil walls. Here we can use this is the parapet and the geogrid. So these two type of materials generally we will use in the flyover, and here geotextile you will use as a suppression layer actually, and this is the drainage layer, aggregate layer. So the main advantage of the application of geosynthetics is there. Here we have to use 600 mm of the aggregate layer, drainage bay. But instead of this 600 mm drainage bay, if I use a geocomposite drain, I can save the 600 mm of the material of the natural resources. So you can save the natural resources indirectly. So application of geosynthetics, because by using the geocomposite, I can eliminate the 600 mm of the natural aggregates. And in the application of geosynthetics for the ground improvement, we can use as a geotextile encased stone columns or geogrid encased stone columns. These are all the improving the ground improvement so that it will improve the bearing capacity. So this is one of the best example of the application of geosynthetics. In runoff patch area, the soil is very slushy, but you have to construct the embankment. In Gujarat sector, entire India-Pakistan border, we have given the design, and they have constructed beautifully the roads along the India-Pakistan border. So this is the condition of the soil. So what we did is, if you won't use any use of geosynthetics, the embankment or road condition will be like this. It will be fully erode because of the water on both sides. And if you use see here, geotextile as a separate layer, then geogrid for improving the bearing capacity. Here we have used the gabion walls. Beside the gabion walls, we have used the geotextile as a separation. And here also rivet matrices. Besides also we have used it. So after using the embankment, you can see the condition. Even the water is there, your road is safe. So use of geosynthetics are very much important, especially in the soft grounds. And even you can use as a capillary cutoff layer. If moisture is there, your embankment will get a frequent potholes. So to avoid that one, you can use as a capillary cutoff layer also. And if your waterlogged area is there, and nowadays we cannot say land is not available, so we have to utilize this area. So what we did is, we have used the geotextile as a separation layer, and then we started putting the fly ash. This is the geotextile layer, and we put the fly ash layer on this one. Then finally we have constructed the embankment. And if the ground is again very soft and you have to put the more loads, here what is the use of that one is, if you use the vertical drains, polymeric drains, your settlement will be very much faster. So what we did is, this is a settlement time it will take without drains. If you use the drains, the settlement will be very faster. Here we have used the PVDs, polymeric vertical drains. This is called stitcher. And so this is the technique we have used in the Visakhapatnam Port Connectivity Project. And these are the PVD drains. Okay. And see, if you use only PVDs and if your ground is soft, it will be failed. So the embankment is failed because of the poor strength. So what we did is, we have used the geotextile as a vessel reinforcement, and then we have constructed the road. We can see here, so this is the way we have used the geotextile as a reinforcement, one point, yeah. And this is the final road surface. Similarly, if you want to use for the hill roads, so if you want to cut the hill slope, you will get many landslides, and you will always see in the news during the rainy season, you will get frequent landslides. So to prevent that one, if I, instead of cutting the slope like this, if I go for a downhill slide as a reinforcement wall, you can get the stable slope. So similarly, you can construct the reinforced soil levels toward the downhill side, like this. So here also a lot of applications of geosynthetics are there. So what are the don'ts? Means technology is there. If you are not using properly, then what will happen? So the thing is, here you can see, if you won't get a proper vegetation, then later it will tear the textile and it won't serve the purpose. At the same time, you can use as erosion control matrix, but the only thing is that if soil is not there, vegetation growth is not there, then it won't serve any purpose. Here also you can see, if the density is not, if you are not compacting soil properly, or you are not laying the geotextile properly, and your thickness of the layer is more, then what will happen? It leads to failure like this. So the thing is that technology is there, material is there, but if you won't improve properly, then the results will be like this. Similarly, if you won't design properly, it will failure also occur. Once if it is failure, again you have to reconstruct only. Similarly, you can see, for protecting the slope they have used the geotextile, but at the same time, the culvert is about top. So what will happen? You have spent the money, but once the discharge is come, the entire material will be waste. So while application, you have to use your mind, and at the same time, you have to give proper designs. So this is the one best example. This geotextile will be backside of the gabion wall, but it is outside of the gabion wall. If it is exposed to sunlight, everyone knows, it will be damaged within 2 years, and it is waste of money also. So we have to use geosynthetics properly. So these are some of the applications you can see. If you won't anchor properly, the entire geotextile is here. So then they will say the technology is flawed, because no one wants to blame from themselves. They will say on the technology. So if you won't anchor properly, you will see here they are not properly anchored at the top. So that's why the result outcome is like this. Similarly, you can see the same way the embankment is eroded, even after implementation. And this is the best example. If you won't anchor, simply they will anchor with this one. If you won't put it in the pit and if you don't anchor properly, once it tears, the entire will be waste of money only. And here we have to use the soil 75 microns, but they are using the boulders. What will happen if you use the material like this? It will cut the geogrid and it will damage. You can see the size of the material. So the thing is that if you won't use the geotextiles properly, nowadays people are using maida for plastering, pasting, that one of some poor quality of gum. The purpose is there, if you won't use them properly, what you will see, the tearing of the geocomposite, the results is there, the fines is coming out at the bottom due to rainwater, and the results is like this, you can see. The entire RE wall at the top is, you will find. So the thing is there, you have to use in a proper way. Similarly, the drainage pipe is cracked so that the fines will come out, only one slide. So if you won't use the proper drainage measures, whatever the RE wall is there, finally it will lead to failure. And if once it fails, again you have to either rebuild or restrengthen, so that you have to spend more money on that. These are some of the failures of the RE walls. And you can see here, the RE wall is failed in the Lithuania is mainly because of the rats. Because the main what they did is that Kuda, that whatever the dustbins is there, they kept just behind the near to the RE wall. So what happened? It made the houses inside the wall, and whenever it gets a time, it will break the geogrid so that the RE wall is failed. And another important factor is there, the boards, it looks like very simple, but it will make houses here inside and it will pull out the aggregates. So that's why what will happen, again the fines will come out and the RE wall will fail. And if your drainage is not proper, the wall may fail. So the main conclusion is that the utilization of geosynthetics can expedite the construction of civil infrastructure. But if your geosynthetics are used in construction, the structural life, strength and conservation of natural resources will increase. But major disasters will result if the structures are poorly built and there is inadequate management or poor implementation. So technology is there readily and it can do many wonders. But at the same time, if you won't improve properly and if you won't manage at the site properly, it will lead to major disasters and finally they will blame on the product rather than implementation. Thank you very much.
Thank you. Thank you. Next page, Kamlesh Rao and Ankush Sharma from Ahmedabad Textile Industry Association.
Thank you, Professor Behra and TIT for providing this opportunity to Atira to present on synergetic flame retardant modification of jute fiber reinforced polyester composites for rolling stock applications. So rolling stock application stands for railways. So here actually it's a joint presentation. I am going to present about the facilities, the incubation facilities and the production and R&D facilities available with Atira. Then I will quickly hand it over to my colleague Dr. Ankush. So a company started by Dr. Vikram Sarabhai, father of Indian space program, in 1950s. We have 4 focus areas. So you can see the focus areas here. First one is research and development, doing product development in composites. Then the other one is training and skill development. We organize training activities and skill development activities for unskilled and also skilled and students and also for professionals. Then the other vertical is incubation. We also incubate startups. So we have been recognized by NTTM, National Technical Textile Mission, to incubate startups in technical textile. So there are around 4 startups being incubated by Atira now in highly advanced areas like functional composites and technical textiles. So the other one is industry integration. Whatever research and development we do, we don't leave it at publication of paper. We also demonstrate pilot production and finally we also hand it over to industry. So recently we have developed a carbon fiber based chassis to an Indian automotive player. That's an example on how we actually scale up the research and development up to the industry integration. So there are many examples. In the interest of time, I'm going to next slide. So these are different areas we work for our R&D, space, defense, then railways and renewable energy. So the composites, I have wider and broader applications. Accordingly, we are also covering all these applications for our new product development. In addition to that, we also have world-class test center. So they can be used in various applications. For example, the infusion we use for developing different space components for ISRO. In the same way, pultrusion we use for different profiles for building and construction. Then weaving and braiding, they are used to come up with glass and carbon based fabrics, either woven fabric or braided fabric for defense applications and even railways. So these are actually images of the facilities we have. So radial braiding, with 176 cents. This is largest radial braiding machine available in India. It was actually established 15 years ago. At that time, it was largest in Asia. We also have weaving for glass and carbon. Then this is the pultrusion machine. You can also see the graphic. It's all about production of continuous length composites. Generally, composites are known for fabricated customized structures, but there is continuous operation also in composites, that is pultrusion, and we do have pilot machine and trial production facility for all these activities that I have mentioned. So these are some more facilities, a compression molding as big as 8 foot into 4 foot with 6 daylight gap of 100 millimeter. We also have solvent impregnation machine for making prepregs. So prepreg is advanced technique in composites to bring uniformity in fabrication. So we do have production machine for solvent prepregs. So this is about testing. So even in testing, we cover all important aspects of testing. So physical testing, mechanical testing, and non-destructive testing. So standards like ISO, ASTM, DEN, these are all the standards we cover, and you can also see some of important test equipment here, like cone colorimeter or flame testing, flame toxicity index. These are some special test equipment available with Akira. So this is a roadmap. By 2030, we are actually focusing to come up with green composites. We already have started work on this natural fiber based composites. Then by 2035 and by 2047, we would like to take part in India's growth story of becoming global composite hub by 2047. Now I would like to hand it over to my colleague Dr. Ankush to start the presentation on technical content.
Some of the part, like what we are doing. This is a small component of that part. So first, like what is the requirement of this flame retardancy into the composite, and specifically why we want to consider natural fiber. So as we know that world is moving towards the sustainable material, and many of the countries are involving that to use the sustainable material in many of the application area, and rolling stock is one of the application area where India need to come and to adopt such kind of material. Now, why? So the growing adoption of the eco-friendly material, fire safety mandate. So as we know that there is a stringent criteria for the railways, like we have to follow certain standards. So right now we don't have any Indian standards, so we are following the European standard, which is EN 45545. So this is very stringent criteria that your natural fiber should, or any composite should follow under those categories, especially fire and safety and perform balance. So once we are talking about improvement of the fire retardancy into the natural fiber composite, so somewhat we have to be compromised with the mechanical performance. So this is also a critical, or I can say, challenge, that without compromising with too much mechanical performance of the composite, how we can improve the fire retardancy in natural fibers. So I'm just skipping this because now this the ultimate objective is to enhance the fire retardancy. Dual phase approach means what? Like right now whatever the composites are coming to the market for the railway application, that is with the matrix modification. Okay, like they are adding some of the fire retardant additive into the matrix itself, and they are using glass fiber majorly. But in order to introduce the natural fiber, as we know that natural fiber, like it can easily catch the fire. So at the fiber level, how we can improve the fire retardancy, ultimately it affects the end performance of a composite. So here effort has been made to improve the fire retardancy at the fabric level, then subsequently at the composite level. So that's why in that way it will be a two-phase approach. Yeah, so fire retardants is not only for the rolling stock application. Wherever we are using the composite, the fire norms are mandated. Whether we talk about the automotive, we talk about the building and construction, we'll talk about the even though the airways. So the different standards are there, out of which railway and the airways having the relatively stringent criteria by which we need to be met. So these are the motivation behind the state. And the challenges, obviously, like balance between the fire retardants and the mechanical property, achieving a uniform dispersion of the FR additives, optimization fiber surface chemistry. These are some of the challenges. Importance of the fire retardancy, as we see that there are so many fire incidents, accidents happening. Okay, and as the demand of lightweight material. So ultimately the people are moving towards the composite material, and we have to be achieve what property we are getting, even the improved performance is required in the composite material. So in that way we have to be work how we can improve the performance. So this is a global demand, right? And thing is that eco-friendly fire retardant. Right now majority of the industries are using halogenated fire retardant, which is again harmful to the environment. So here what we are trying to do, we are just trying to use non-halogenated fire retardant, so that it can also be considered under the sustainable material. So these are the different standards which will be used in the different application area like aerospace, railways, automotive, marine, civil and building. So specifically, initially we have targeted EN 45545, which is as per the railway standard. However, during the research, whatever the results we are coming, that can be applicable in the different application areas. This slide gives an overview of the flame retardants, like what are the different kinds of flame retardants, and then what are which are the eco-friendly and which are the non-environmental friendly, and what is their characteristics and how they are compounding. So there are certain non-halogenated fire retardants like phosphorus based, ammonia based, phosphorus nitrogen based. So these kind of the things now people are started to be used, and in that way we need to be achieve the fire retardancy into the composite. I'm just skipping this, coming on the work. So the material unsaturated polyester resin, initially jute fiber. However, there are so many new age fibers are coming, as we already heard in the innovation session. So new age fibers are coming, and then application of the new age fiber is also there. So right now, as the jute is available in abundant quantity, so we have considered jute as a reinforcement material, and this is the approach like the fiber surface treatment, the matrix modification, and the composite. This is a process flow chart like how it has been done. So that simply pet dry process has been adopted. So whatever the fire retardant additives has been done, we consider also the water, distilled water as a dispersal media. Okay, so make it more environmental friendly. And then with the pet dry machine, and then it has been tested. In the coming slide, I can show you so how we have achieved the fire retardancy into it. So if it works, I don't know. Yeah. So you can see here. This is as per the ISO standard. We have tried with the both woven and non-woven structure. So you can see this ignition time is 0. I can say it is self-extributed. Okay, so with this is with the treatment at the fabric surface or fabric level treatment. This is with the non-woven. So you can see it is self-extributed immediately after just removing the fire. It is self-extinguishing, and not a single spread of flame that has been observed. So with that, we have just considered different kind of the fire retardant, non-halogenated kind of fire retardant, and then different weight percentage, and then we have to see that what are the extinction time for that, and that combination has been adopted to make the composites. So I'll just skip these videos now. Okay, so this is a simple process for the composite making process. So we adopted compression molding process to make the composite, and the different test has been performed as per the EN 4554, which is one of the 1 calorimeter, UL 94. Limiting oxygen release is also be adopted, and what we can see that we have achieved so far in 1 or 2 combination is HL3. HL3 is very stringent criteria. So as per the EN 4554 R7 clause, at the 50 kilowatt per meter square, the radiant heat is up there. and in that case your composite should not be catch the fire. So we are able to be achieved with the natural fiber, and further we are trying to improve the performance of that. So these are the results for that. And what we have seen that the combination of the fabric treatment as well as subsequent adding the fire additives into the composite, we are getting the additional benefit so that it can be fulfill the criteria. So synergy effect, obviously it is benefiting. These are some certain technical risks. So mechanical property has already been discussed. So research is ongoing how to improve the mechanical performance without compromising the fire retardancy as well. So in general case, it is 85 to 90% strength that we can get out of 100%. Then the supply chain, market research, and the regulations. So these are certain in general points. What in order to implement this system, what the things need to do. This is like for like what the global benchmarking related to the natural fiber composite. So India is having by having this kind of the material and implementing into the railway, because we have the vast railway network and day by day new materials required. So obviously it is also helpful for the economical point of view and the business point of view for the India. These are some future directions. So obviously what Professor Arjuna mentioned, that CNT, so CNT or graphene is also helpful to increase the mechanical performance. It is also helpful to enhance up to certain level of fire retardancy. So that effort is also we are doing at our place by having the coating of the CNT and the graphene on the natural fibers. Skipping this. So with that conclusion, so dual synergy effect is helpful to improve the fire retardancy into the natural fiber composite, and ultimately that we are able to be achieved up to HL3. And with other natural fibers we are also trying, and this project already we are working with one of the railway component manufacturing. So like we are going to be approached to the Indian Railway, specifically RDSO and ICF, for proposing this materials. With that, thank you.
Thank you. Nothing. Flame retardancy, very important. So I request Dr. Chalman, please come for a photo and accept the certificate.
हाँ जी सर, हाँ yes.
And thank you to the audience for being supportive. Now it will be split into 3 parallel sessions. One session will continue here. So announcement
before the evaluation committee. After the parallel sessions, tea will be served during the poster presentation. A cultural function is being organized immediately after the poster presentation, and that would be in the same hall. And that will be followed through the conference dinner will be served after the cultural function. I request to the audience that some parallel sessions are going to be start, and audience feel free to move LT1 or LT2 based on their interest. So now the third session is going to start.
I am a research scholar under the Professor SPC and the PK Vera. I am from the I-Pole impact and results and conclusion. You can see in the video, in the top host video, this is a vehicle which damaged during the impact on the wall. This is a pole side impact, this is a front impact. Generally I will discuss about the multiple impact and pole side impact, how the metallic part is damaged during the impact. In introduction, side impact account for a large percentage of severe automatic injuries, and multiple impact and pole side impact are highly critical crash scenario. And generally, we are using composite in the place of metallic parts. Generally, composite have lightweight design and energy absorption and passenger safeties. Generally, we are using the FEM methods to find out the most energy absorbing materials. Then final element analysis helps to simulate crash scenario before physical testings. These are basic process for the FEM modeling technique. In FEM modeling technique, there are 3 types of process. First one is pre-processing phase, and second solution phase, and third one is post-processing phase. These are the different conditions to define the meshing, then boundary conditions. The material property is very complex for the composite materials. And then after that, the solution. You can see the video how to damage the ball on the cubes. Now come to the meshing of the object. There are number of elements, bar element, square element, cell element, solid element. There are different type of elements we are using to categorize the complex composite parts. These are the boundaries. This is very essential for the molding of the composite materials. You can see in the figures there are one block we give the force in this direction, and this part has fixed. Means there are lots of boundary conditions according to the impact scenario. Now come to the material property. In the material property there are different type of properties. One is elastic properties, basic properties of the fibers, fiber and epoxy composite, and another is plastic properties. Plastic property is very important to see the how composite is damaged during the impact or crash analysis. These are the plastic properties, and these are the elastic properties of the material. We can find out the different properties using the basic test of the composite material. These are the tensile and compressive and shear test for the getting these properties for the composite materials. Now come to the full scale molding of the automotive fender. Generally, we compare the 2D, UD, 2D and 3D composite. This is a UD composite. You can see in the UD composite there are delamination occur in middle of the two layers. One in middle of the two layers. In same as it is in the 2D composite, you can see the delamination in between two layers. In 3D composite, there are no delamination, only damage. You can see there are no any delamination. You can see only the damage in the middle portion of the composites. So we are using 3D composite as the place of the metallic parts of the automotives. Now come to the impact of the fender. This is a fender of the automotive structure. This is a fender basically used to protect the wheels. I am using 6.2 millisecond for experimental literature for the impact of the fenders. This is the impactor, this is a fender. Fender dimension is 1 by 0.7 meter, and all edges are fixed. All edges are fixed. First, I simulate the using the steels. These are the value of the steels. You can see this is black one is experimental and red one is numerical. You can see the variation of the forces. In steel, they easily dented during the impact. In single impact, easily dented. Video is not working, I think. You can see the damage area of the impact. It is fully dented during the impact. Now you can see that on the composite material, you can see this video. This is after this is first impact, second impact, and third impact. After multiple impact, the composite is not damaged. These are the result of the multiple impact of the composite fender. This is for the first impact, this is for second impact, this is for third impact, and this is for fourth impact. The composite little bit damaged in the fourth impact, but in steel this is fully damaged. Now come to the comparison between the forces values. This is a blue one for the steel materials, this is for the composite materials. In composite materials, force is very less as compared to the steels. Now come to the pole side impact. This is a pole side impact. This one is a pole. this will be vaguely impacted to the pole. You can see the finger is impacted to the pole, and steel is fully dented in this case. Steel is fully dented, and 3D well is little bit damaged in the middle portion. You can see the acceleration value for the 8 millisecond, a meter per second. Steel have higher acceleration, and 3D woven composite less acceleration, and steel is sharp point and damage the occupant easily. This is for the steel, this for the 3D woven composite. Now come to the conclusion. We compare three types of composite, UD, 2D and 3D, and found that the 3D is better as compared to the energy absorption. Now we are doing some FEM analysis between the steel and composite, and we get the steel is dented and single impact, but the composite is not dented as a multiple 4 type impacts. And pole side in the pole side impact acceleration value is higher in the steel, but in the composite the acceleration value is very less as compared to the steel. That's it.
सामने हाँ यस सर
Very good afternoon to the august audience. Myself, speaking from the Mechanical Engineering Department of IIT Delhi. So, the topic which I will be speaking on is on design and development of composite shafts. This work we started, long ago, around 20 years ago, but it was not done in a continuous manner. My own work research was on composite shafts with the rotodynamic analysis. Thereafter, we, did some projects for design of composite shafts, and then creating the joints. I'll just in this presentation I'll just list some of the. And Sandeep Kumar worked on the design of shaft joints. Gubran worked on the stresses and layers, and Patil also worked on delamination aspects and design aspects. So in this part, of course, we all know that fibrous composites, particulate composites we are tackling, but we also listed laminated composite as a separate category. The reason being that when we are dealing with the shafts, you could make a shaft from a filament winding process and with some angles. There are layers. That shaft is also a laminate. You could give different angles to different layers. But especially it was found in the case of composite drive shafts which were used in automobiles, that when the vehicle is moving on and then due to some pebble striking or due to, from the some impact from the road, the shafts got damaged. So people also tried to use the metallic shaft. It was a composite shaft. One of the solutions which has been proposed, the metallic shaft with an aluminium sheet on the top. So in order to avoid the damage due to low velocity impact. So when we talk about the composite shafts, it's not that the shaft, every shaft in the industry being used is to be made from composite shafts. There are only some niche applications where it is beneficial to use the composite shaft. One of the applications is this ship propeller shaft. And the other two applications where we are using is this is the helicopter tail rotor drive shaft and automotive drive shaft for a truck. Now, if you look at all the three shafts, this shaft is for the other two applications where composite materials are have been explored in detail. It's not for any general kind of industrial shaft. These are the shafts. What are these three pictures have in common? The picture which they have, the thing which they have in common is that the length of the shaft is very large compared to its diameter. For example, in this this is the helicopter tail rotor shaft. The engine is at the front while the rotor is being taken. The drive is taken all the way to the end of the helicopter, which almost like 6 or 7 bearings in between. The similar is also the case with the ship propeller shaft. The propeller is here. You have the stern tube and the forward bearing, aft bearing, and then there are a lot of it goes for a fairly long amount of length, almost like we have seen like shafts like 10 meter, 20 meter, that long shafts are there. So it is those applications where the shaft length is quite large compared to the diameter that composites becomes a viable criterion. Why it scores over steel, especially in those cases, is because we know that composites have got higher stiffness to weight ratio, and for the case of long shaft, one of the problems has always been the lower value of the critical speed. In the critical speed on the top, if you look at it, the expression for critical speed is basically K by M. On the top is the stiffness, on those sides mass. So you get benefited from both the sides. It's actually that ratio that directly counts. For example, in the case of this ship, this helicopter tail rotor, this is once you have this shaft from metallic, made from steel, let's say, even if it is a hollow shaft, one has to put in a large number of intermediate bearings. You can see that 1, 2, 3, 4, 5, 6, 5 to 6 bearings are there. Because in order to increase the critical speed, but if the same shaft is made from a composite material, it will have higher natural frequencies naturally, because of the stiffness to weight ratio is 5 to 6 times higher. As a result of that, you can even, apart from reducing the weight of the shaft, you also indirectly reduce the weight by reducing the number of bearings. The same thing also happened for a ship propeller shaft, that you can use now longer stretches of shaft without intermediate supports, and each intermediate supports it costs weight, it costs in terms of the money, and it also costs in terms of maintenance. Okay, so if you can reduce the intermediate supports by 1 or 2 or 3, it's a huge saving, overall saving. So these are the applications where composite shafts are found viable. So what we did in this study was was a design of a propeller shaft, ship propeller shaft. Similar is also the case for a automotive drive shafts. So a drive shaft which is long enough, there only if you are using for example, it's a front engine front wheel drive, we don't use a composite propeller shaft, but it's a front engine rear wheel drive, where a long drive shaft is required. In those cases, we use which is the case of light trucks, army trucks, where the shaft is so long it has to be made in 2 parts and with intermediate support. So there also automotive drive shaft is also in the same application. So when we talk about the design of the propeller shaft, this was again one of the projects which we had done. So what because the shaft, what happens in the case of a propeller shaft is that when there might be some weights or gears or various components attached to the shafts. So what happens is that when the shaft is rotating, each axis of the shaft, each fiber of the shaft, which I say, let's say in terms of axis, when it's at the top level, it undergoes alternative, each element of the shaft undergoes alternative tension and compression even when the load is stationary, because it's a gravity loading. So because of that, the delamation happens and failure happens because of this, when the shaft is undergoing tension and compression, and most importantly the fatigue failure happens. Okay, so we designed the shaft, this was a program, I cannot present the details, this was a program which was given for a naval warships. So they made a design finally of the composite material, and the fatigue design part was performed in our lab. So I'll just do the basic methodology is that there are primary two kinds of loading in a composite shaft. One of them is the weight of the various components and also the self weight of the shaft. That is the one loading which is given, and second is the unbalanced masses, unbalance in the shaft at various locations. The unbalance is what, in fact, unbalance, although it's a rotating load, it rotates along with the shaft rotation. For any particular element inside the shaft, it is giving you stationary load, it's giving you mean load. Whereas those loads which are stationary, like the gravity load, they are the one which are giving you the fatigue loading. So what we did finally was that we, for any particular shaft, the finite element analysis was carried out, and the alternating stresses and the mean stresses were evaluated, and accordingly for composites we have from the SN diagram one can find out the particular stacking sequence. In fact, here also for each layer of the composite shaft one needs to find out what are the stresses, the mean stresses as well as the alternating stresses, and accordingly the fatigue life of each layer is made kind of uniform and the layers are proposed in such a manner. Then once the shaft is there, if you look at the this diagram on the right side, so whenever we're using composite shaft, the composite shaft is not directly connected with the engine or with the prime mover. Always there are going to be small sub shafts. Here this covered. Okay, so this one is metallic part, and this one is a composite, hollow composite shaft. So here there is some covering, but in between one needs to design this joint of metal to composite. This has been a serious consideration, and we'll see later also, this joint is one which leads to stress concentrations and becomes the reason of the failure. So what we did was that we did the optimal design of, so what we did it was again by finite element analysis, what we did was that for a particular case when the shaft is under torsional loading, okay, as well as under axial loading, one can design what should be the, because this is just one typical element, but it should be actually the complete row, complete circumference. It represents this thing going to complete. So how many boards? So there are three things to be designed. One is that what should be the distance from the end of the shaft. So what we are doing is that inside the shaft, inside we have a solid stub shaft. Outside we have a hollow composite shaft. Okay. So there is a friction contact we maintain, but that is not sufficient. If any failure takes place, it will fail. So we need to put some bolted joints. Okay. So where those screws are to be put, how many number of screws should be put, how many rows of those screws are to be put, and what should be the diameter of the screw, so that for each screw we are drilling a hole, as you can see. So once this hole is there, then around this hole there will be stress concentration, and the distance between the holes should be such that the stress concentration region 1 should not interfere with the other, the concentration of the other, and so accordingly we decide how much should be the distance. So this is for a typical dimension. We have design this for diameter of 8, this distance is 4, 8, this is 12, this is 4. Okay, so one has to design the joints, the joint location. Joint means the bolted joints and the screw joints which will go into the stub shaft. Okay. So that was one option which we, so whenever we are doing now composite shaft, we are using those particular joint specifications. And then currently, along with my colleagues, we are doing buckling analysis of composite shafts. So in buckling, what happens is, because most of these shafts are hollow shafts, so whenever they will be under torsional loading, they are going to fail by buckling. So of course delamination also happens, which we have studied separately, but in the buckling case, the buckling pattern will be formed. So for that purpose, what we have done is that, you can see here, these are the stub shafts, they are connected with the stub shaft. So this is the way, for example, this one is a carbon shaft. These are the two stub shafts. The stub shafts have, at the end of the stub shafts have been deliberately made square shape, because so that we can load them in torsion. We want to do the testing. So this is a torsion testing machine, where the shaft will be loaded, and it will be, the chuck will be rotated one side, fixing one of the side. And accordingly, one can see the buckling pattern, that some of the shafts you can see they are failing by cracking, some of the shafts will be failing at the joints, some of the shafts will be failing by a proper buckling pattern. So this is actually the desired failure of the shaft, that buckling pattern should form. Okay, and so we did this analysis, and accordingly we have estimated. So these are the equation. These are the graphs for torque versus the twist angle, and the buckling point is also noted down. And we have tested this with the theoretical analysis in Avecus. We did the buckling analysis for these shafts. And the aim is primarily to have a comparison of the different, from buckling point of view, to have a comparison of the different combinations of the materials, because each material has its own ductility, its own modulus, its own failure strength values. So, for example, this one is aluminium, carbon, Kevlar. A combination of that is the one which is giving you a specific curve, and aluminium 2 layers, carbon 5 layers, and Kevlar 1 layer is the one which is giving you the maximum buckling torque. So one can design. So our goal was to basically again to propose the configuration which is going to give us the best. So these are again some of the results. For example, these are different modes of the shafts. Then we have, for the case of buckling, you can see there in this diagram a buckling pattern, zoom view. A buckling pattern has started at one of the locations, and so this is what we predicted from the. So the work is still going on. One of the aspects which we are currently studying is on the low velocity impact of these shafts. So I just had an overview of what are the various issues when we are using composite shaft. First of all, the composite shaft are to be used only in those cases where we have where we want significant length to diameter length to diameter advantage. Otherwise, in short small shaft, I wouldn't say composite shaft should be used. Okay. So the design is based. So we established a methodology based on for the design of the composite shafts using finite element as analysis and the fatigue equations. Okay, and then special care is also needed to create the joints between the metallic and the stub shafts. And the buckling failure analysis has been conducted at the match with the theoretical analytical calculations, and then based on that. The optimal configuration is also recommended. Thank you. I would welcome questions. Yes. done is that if you look at this, so this is the combination is aluminium, carbon, Kevlar and glass. So we have not analyzed from the techno-commercial point of view.
Okay, but technically,
one of the best is the carbon composite shaft compared to Kevlar or glass. But in order to reduce the cost, we have also used, we means not me, but some other researchers have used combination of glass and carbon along with an aluminium sheet. The top layer is basically aluminium. So that they have found, we have not done that study, that they have found that gives you very good impact resistance especially for the case of propeller shafts. We do small pebbles.
And if it is not impinging on your IPR, sir, just small question. If I use it in a submarine kind of situation, where the sonar signals are very important, you want minimum sonar signals.
In fact, for the naval project, their motivation was to reduce the signature.
Okay. So what's the result? The result, end result.
The end result was they have used in one of the ships. I don't know whether it because it was one of their goals to use composites was to reduce the signature from the stealth point of view.
Thank you.
So
you can continue.
Yeah, we can discuss that. We can discuss that.
Next presenter.
Hanji sir. Hanji sir.
Good afternoon, one and all present over here. I am Dr. Vibhu Krishna Das, belonging to Department of Textile Engineering, Odisha University of Technology and Research, Bhubaneswar. For last almost more than 15 years, I have been working with composites, particularly three-dimensional composites, jute, coir, sea-silk, hybrid, fiber reinforced composites. Last 15 years I have spent almost playing with the architecture, fiber architecture from two-dimensional to three-dimensional structure, varying the resin. And currently I am going to present some of my experiments with the third element, that is the feeler, that is the coconut cell biacher. Which has been prepared and used with natural fiber composite. The natural fiber was a hybrid of jute, coir and sea-silk. But before I proceed, let me introduce myself. I am from the eastern coast of the nation, that is the state of Odisha. And in Odisha, the state capital is Bhubaneswar, where my institute is placed. You can see OUTR, Odisha University of Technology and Research. The Bhubaneswar city is known as the city of temples. So you can see a lot of temples which surrounds our university. Many Hindu temples. This is the Buddhist temple that is available in Bhubaneswar. I would like to invite you to have a visit to these archaeological sites also. Jain caves, Hinduism, Buddhism and Jainism all were available in ancient Bhubaneswar. This is the department constituency, that is we are running UG from 1994, PG from 2015 and PhD program from 2021. The outline of my presentation will be like this. Coming to the motivation part, why did we go for presenting or investigating? It is regarding the sustainable engineering materials, where we have used natural fiber composites. Jute, coir and sea-silk all are available in the coastal city of Bhubaneswar, which are renewable and to some extent waste products from farming. The coconut cell biacher is a functional feeler which can enhance the mechanical strength, dimensional stability and moisture resistance. Moisture resistance is one of the key bottlenecks of natural fibers which lose strength due to presence of moisture. This study aims to transform agricultural waste also, because sometimes people throw these fibers out of agriculture. So what are the leads for coconut shell biochar? Coconut shell biochar are rigid carbon-rich filler that enhances the tensile and flexural strength by improving stress transfer within the composite. It reduces the moisture diffusion pathways, so thereby improving the dimensional stability. The porous microstructure of biochar promotes better mechanical interlocking and fiber matrix interfacial bonding. These are derived from agricultural waste, coconut shell. Those are normally thrown away after use, which supports sustainability. And addition of coconut shell biochar CSB, I can say, improves the thermal resistance of the composites. So if I summarize, then we are going to introduce or we are working on introducing these coconut shell biochar to the hybrid composite, and then evaluate the water absorption properties and moisture diffusion behavior, to analyze mechanical properties like tensile, flexural and impact properties, to investigate the combined effect of fiber hybridization and biochar loading, that is having two different percentages of biochar on overall mechanical and durability performance, and the study of morphology of the hybrid composite after it is tested. So these are about the raw material that we have been using. Jute, coir and sisal, which are treated with 5% sodium hydroxide at room temperature to remove the lignin. Then rinsed with neutral water to get the neutral pH, then air dried, oven dried, and used for composite manufacturing. This is the proposal for biochar preparation. Pyrolyzed at 600 degrees Celsius, coconut shells were ground and sieved to get a coconut shell biochar. This is the composite fabrication that was made with compression molding machine. Needle punched hybrid fiber wave was prepared in the card. Then epoxy and biochar, they were sonicated and applied on compression molding machine. Cured composites were cut for different testing conditions. This is all about the specification of composites. This is part of the research. So I have shown only 4 composites. In fact, we prepared almost 30 with different variability. So this is the different weight fractions. Those are used, and you can get the fiber volume fraction of 52 and 55%, which is quite good. These are the different characterization techniques that were followed for water absorption, tensile, flexural and impact properties. We also went for TGA and APSM imaging after the testing. So water absorption test was conducted according to STM D570-98, and the immersion was up to 120 hours. Water uptake was calculated with this formula. You can see the graphs which shows the water absorption increases over the time, that is from 20 hours to 120 hours, and the JCS2 composite that was having highest water absorption, almost 1.4%, and the JCS4 was the third lowest due to the barrier effect of biochar, which was loaded with 10% of the biochar. So the natural fiber absorb moisture due to presence of hydroxyl groups, and these coconut shell biochar helps it to develop diffusion pathways, which was found in JCS4 composite. Improved fiber matrix bonding, which reduces the absorption of moisture. The tensile testing was done in a Instron 5966 machine with 10 kN capacity with a cross-rate speed of 5 mm per minute. And The results are here. You can see the results with dry condition as well as the wet condition. So you can see the reduction in strength, that is almost lowest for JCS4, which was having 10% of the voucher as loading. Flexural testing was also done with 3-point bending method and with the same machine with the cross-head speed of 2 mm per minute. You can see the flexural strength results for both dry and wet condition that we went for, and you can see the dry strength is always better except JCS3. Okay, and in wet condition the JCS4 is having the good retention, almost better than all others. The impact testing was done in IZOD impact tester with 25 joule capacity, and you can see the results. Yes, I'll be completing soon. So the dry versus wet strength results were compared, and it was seen that wet condition improves the impact energy absorption due to biochar inclusion, which was very good and encouraging. And the sample JCS3 exhibits highest wet impact strength of almost 58 kJ per meter square. And we went for thermal analysis, that is TGA, up to 850 degrees Celsius we went, and the graphs obtained were like this. You can see up to 400 degrees Celsius we saw that the principal degradation happened, and JCS4 shows the highest thermal stability, having higher fiber volume fraction and biochar content. We did the imaging of our impact strength tested samples in the FESM that is available in the university, and we saw that 4 different images were captured for JCS1, 2, 3 and 4. You can see it has been mentioned here, the sample name JCS1, JCS2, JCS3 and JCS4. So you can see the fiber pull-out and voids in JCS1 and micro cracks. These are all samples were tested, were imaged after the impact testing. You can see fewer voids and better adhesion was observed in the JCS4 sample, which was having 55% fiber volume fraction and 10% of the biochar. So we can conclude that void reduction from coconut cell biochar has been
today, and I am pursuing my PhD under Professor D. Mehra and Professor S.P. Some machine learning insights. So, additive manufacturing, popularly known as 3D printing, is a process of manufacturing 3-dimensional objects from a 3D CAD model data. It is opposite to modern subtractive manufacturing, and it uses variety of materials in the form of liquid resins, solid filaments and powders. And to make a product, we first design CAD model, then we convert it into STL format, then we slice it, and we make G codes, and then we give it to the 3D printer. So dynamic mechanical analysis. So it is a technique used to analyze mechanical properties, especially response of a material to an oscillating either stress or strain input as a function of temperature, time and frequency, or combination of these parameters. It is valuable for polymers, rubbers, composites and biomaterials. If you are applying sinusoidal force, then you will measure strain, deformation and vice versa. And it often performed over a range of temperatures to study materials behavior under different thermal conditions. So these are 3 main properties which are measured in DMA, dynamic mechanical analysis. Storage modulus, which is material's ability to store elastic energy. Loss modulus, it's material's ability to dissipate energy as a heat.
and damping factor, which is a ratio of loss modular to storage modulus. So this was the working methodology. I used nylon carbon filament, and with the FDM 3D printer I printed composite samples. Then I performed dynamic mechanical analysis in 3-point bending mode, and then I took that data and applied machine learning models to optimize my printing parameters and to know which parameters affected the more dynamic mechanical property. So these were the curves, storage modulus versus temperature. So basically I printed 27 specimens with the different printing parameters. So these are the combinations. So I wanted to see which in which curve the storage modulus is high. So if storage modulus is high, then that material is more stiff. So in this, you can see in the pink one, we got the high storage modulus. So there are a few things, like I would always not want that my storage modulus should be high. It depends on the application. So if you have high storage modulus, then the applications are different. If you have medium storage modulus, then the applications are different. And for similarly low storage modulus, the applications are different. In loss modulus, its material ability to dissipate energy as a heat. So similar case for loss modulus also. So in my case, I would want lower loss modulus. These are the loss modulus applications. So its functional meaning is vibration damping, and in 3D printing applications, it's used in isolators, damping inserts, as housings, and several fixtures and jigs. Damping factor. So damping factor is the ratio of loss modulus to the storage modulus, and it indicates how effectively a material damps vibrations by dissipating energy relative to elastic storage. These are the damping factor applications. In 3D printing specifically, there are 3D printed dampers, lattice-based energy absorbers as well. General purpose 3D printed functional parts, load bearing carbon fiber reinforced 3D printed components, and stiff frames. Then it comes to machine learning. So I was having 4 variable printing parameters, which were layer height, infill printing temperature, and infill density. So M dash was storage modulus, and double dash was either you can either denote it by E dash or M dash. So M double dash is loss modulus, 10 delta is damping factor. So these are the function of these 4 infill patterns, input parameters, and F M dash, F M double dash, and F and delta is your machine learning model, how it was trained, and E is the error between the experimental data and the machine learning predicted data. So I used 9 machine learning models to train this and to get how much error I am getting. So you can see that it is predicted on y-axis predicted data, and on x-axis there is the actual experimental data. So if your data is coming on the 45-degree line, that model is your best machine learning model. So in my case, I used 9 machine learning models from all families, and there is a MLP model, multi-layer perceptron, which is a artificial neural network, a feed-forward model. This was giving a higher R-square value of 0.997. So this model was the best model, and I chose MLP for storage modulus. As you can see, 0.9 R-square value of the MLP. Similarly for loss modulus, MLP gives the highest R-square value, so I chose MLP for loss modulus as well. For 10 delta, you can see the data is not, in several models the data is not plotting good on the 45-degree line. So for 10 delta, I chose HGB, which is a histogram based boosting regression ML model. So this I got from this machine learning thing. So I got to know that which parameter is affecting my property in how much manner. So the best parameter was test temperature, because it is a testing parameter, so it will be giving the best value in all 3 cases. But the input parameter, which was 3 layer height, infill temperature, infill density. So for storage modules, you got to see that layer height, infill temperature, and infill density. Similar pattern in loss modulus, but in 10 delta you can see layer height, infill density is upper, and then infill temperature is low. So you can see what parameter is affecting in how, in what manner on your dash property. So this was a beauty of the machine learning models. So with the you can see with these models that you expect the dots are showing the experimental data and the line is your predicted curve by the machine learning model. So you can see the all three curves at 90% infill density, 95 and 100. I just checked how well my machine learning model is predicting with respect to my experimental data, and it is fitting, the curve is fitting between the experimental data. Similarly, as you can see, that predicted ones, this curve tells you, you can predict at new infill density. So my data was having 90, 95 and 100. This was the experimental data which I tested. But now you can predict a new data curve at new input parameter. Like 92.5 was not in my experimental data, but I predicted this new curve at 92.5 and 97.5. So this was the, again I would say, beauty of the ML. Thank you.
Some basic questions. Typical civil structure is based on columns and load-bearing columns and beams. So how the load distribution takes place in case when you are doing this additive kind of civil construction?
So in the columns, the science is totally different. Like you are talking about the vertical columns, right?
Vertical columns, horizontal beams, and all that.
Yeah, the column is a different thing. My parameter was the for those parts which are subjected to 3-point bending mode. So column is subjected to always buckling. Like if you would see in civil engineering applications, it would always subjected to buckling.
Yeah.
So if a vertical column is there and the load is downwards, so it will bend like this. Like it's a vertical column, it will either bend like this or bend like this. So this is a separate case, and it is not subjected to 3-point bending. If you talk about this girder or this like beam, then it is being subjected, because in the front, at the top, in the center, if you apply that load, that is also a static load. I was talking about dynamic loading. So if like in cars, you drive a car, so there are the suspension springs where the dynamic loading, like you drive the car, there are so many obstacles in between. So the spring and dashboard systems are there. So this is for those parts.
And for techno-commercially speaking, with what kind of construction, 1-story, 2-story, 3-story, it makes techno-commercial sense?
It doesn't belong to construction thing. It is either a polymer parts which are being used in either automobile or aerospace. So there are so many parts, 3D printed parts, which are still being used in aerospace. So for those applications we use this, and where the part is subjected to different thermal conditions.
Thank you.
Hanji sir. Yes.
Respected chairperson, delegates, colleagues and friends. Myself, Dr. Uminder Singh. I am a family member of Steelbird Helmets, and now I did PhD at IIT Delhi and research under the guidance of Professor B.K. Behra on the topic that helmet impacts biomechanics. So today our topic. So this is the overview of my presentation: introduction, intra-layer approach, research objective, material and methodology, result discussion, and conclusion. So coming to the background and motivation. So firstly, as you know, helmet, if we talk about the human safety, then helmet is a protective headgear which can protect you when you are riding two-wheelers. So in helmets there are three major components that act as a primary role and protects your head. So the first component is helmet shell. So helmet shell is the outermost layer which provides, like during an impact, that transfer the impact load towards the helmet liner. So helmet liner is a secondary layer, which absorb the impact load and dissipate throughout the area. And another one is the retention. So if you have securely fit the retention system, that is the buckle, so you can secure your riding when you ride in two-wheelers. So our main focus is on helmet shell, that is the outermost layer of the helmet. So in helmet shell, basically there are the two processes for development of helmet shell. One is a fiber reinforced composite shell and another is the injection molded polymeric shell. So I am concerning here about the fiber reinforced composite shell because in plastic molded helmet shell we have to maintain, if we have to maintain that particular standard, where the thickness is like 3 to 4 mm. So in case of fiber reinforced helmet shell, the thickness could be reduced up to 2 mm, and also we got some high strength and low weight composites. So this is the role of helmet shell, as I already mentioned, that distribute the localized impact load, prevent the penetration and control the peak acceleration. So coming to our research objective, design the lightweight hybrid composite helmet shell, fabrication of interlayer and intralayer hybridization, evaluate the energy absorption, peak impact force, damage morphology and aerial density, and identify the optimal stacking configuration for next generation cell. So these are the material we utilize: the Kevlar, carbon fiber, Dyneema and Xylon, and also matrix we are using epoxy that have viscosity 1000 to 1500 megapascal. Coming to our main research focus, like inter and intralayer hybrid approach. So we are trying to develop the lightweight helmet shell using inter and intralayer hybrid approach, in which on the back side we utilize the various fibers, that Kevlar, carbon, Dyneema, Xylon. So, and also that is the interlayer hybridization. Apart from this, we stacking the layering as interlayer hybridization, in which you can see here the Kevlar and hybridization, interlayer hybridization of a 3 merge, and we form the laminates, and we accordingly the laminated composite is balloon molded, as you can see on the as a base layer, and after that we did some impact test to identify that is it like is it giving us a strong benchmark as or having some dynamic impact loading conditions. So here, after the impact testing, we tried with 12 samples with different stacking sequence, stacking laminates, and different as you we are utilizing the different interlayer hybridization approach. After that, we analyze the damage morphology using the microcity analysis, and as you see here, this is like impact penetration test according to Federal Motor Vehicle of 218 DOT standard. So in that standard, the penetration of that helmet shell, the strikers penetrate from the 3 meter fall. So here the bulge zone we have to calculate, like after that peak acceleration we calculate the bulge zone, that liners not after the liner the striker not penetrate to the head skull, so that the bulge zone could be evaluated after the impact test. So in impacts we assess the force versus time, force versus displacement, and energy versus time, and these are the some impact test results of all 12 samples, in which we found that Dyneema Kevlar based interlayer hybridization along with carbon layering provides the flexible like 3078 peak force, and also Dyneema Kevlar plus Xylon Kevlar interlayer hybridization shows the 3692 peak force, and mostly the samples that carbon having with Xylon and Dyneema combination provides a higher peak force and displacement observed, and also the total energy absorption with a minimum thickness. So as we observed after the impact test, the bulge zone that we want to evaluate to know about that how much impacts to the helmet skull is going on after this testing. So these bulge zone evaluate according to the scale like deflection behaviors, and we also try to analyze in microscopic analysis that either what damage behavior when we impact. So is it damage to the interlayer hybridization of the fiber to matrix interface, or what exact? So here you can see the fibers as you see A is fiber fracture and B is interlaminar delamination. So here you can clearly see that the delamination occur due to when the impact is occur and the fiber matrix interface is somehow like deflect. So matrix cracking is also visible on C and ply failure you can see here. This is the microcity imaging which clearly shows that after the impact that how it behaves. So it behaves under this impact loading and how much bulge zone it created exactly. So this microcity help us to identify that how much bulge zone created and how much it resists to penetrate to the human head skull. So now coming to the conclusion. So conclusion is like the superior hybrid configuration identified using the interlayer hybridization. Sample 10 having the Dyneema and Xylon combinations laminate emerged as the optimal material architecture, and it achieved the peak impact force of 3692 Newton and demonstrated the total energy absorption of 39 Joule. And so the study confirmed that the strategic stacking sequence of high performance fiber minimize the back face deformation as you can we mentioned through this microcity time analysis, so directly reducing the risk of blunt force trauma to the bearer. So thank you.
Do you have sample of this helmet here or?
No, we don't have.
Okay. Then second point is that in a Formula cars, there is a typical impact could be there.
Right.
And this simulates the condition of a helmet also. So
yeah.
If we use this grid or the covering of the driver with this kind of 3D whatever you call it helmet, will it protect the?
That we are also doing that in Formula FIM standards.
Okay.
The impact speed is 8.2 meter per second.
Okay.
That also depends on the different targeted locations.
No, I'm not talking about the helmet. I'm talking about the driver covering as such.
Yeah, definitely. Our main objective is to make it lightweight and provides the impact strength.
So you will build in the Formula 1 car structure?
Yeah, we can also, through this approach, one can try this with Formula 1 racing cars.
You are working on that?
No, we are not working. We are only working with helmets.
Okay, let's work on that.
Yeah, sure.
Presentation, could you please use not secrets about parameters of lamination, technical parameters, how long maybe of special rules, because it's not easy get good samples for future.
So basically, we are trying here to make it like more lightweight, because in helmet standards, the lightweight with enough protection is our main focus. So at that we also tried with some like technical parameters if you are talking. So in that case we have the EPI and PPI of a 30 ends per inch and 30 picks per inch. So that's, yeah, that is the same approach. So you can also try with like more or less in the range. So that provides the efficient energy absorption property.
Thank you very much.
Yeah.
Wearing helmet is a big problem with
Comfort.
heat, yeah, comfort. So have you a model where you have got air ventilation provision also?
Yes, we are also working with comfort level, and even if we talk about that high-end products, so we are developing some like a state of chamber in which we are evaluating with numbers of candidates are there, so they evaluate different types of comfort levels. Also we have a Kawabata evaluation systems to analysis, and we are also means we are trying to make it more comfortable with premium helmets. As you are now aware that India has a very large population and affordability is a main matter.
I have a solution here, sir.
So affordability is a main matter. So if we talk about the 5 rupees, yes please.
No, I'm answering here.
Yeah. Okay, that's my.
हाँ जी हाँ yes sir. Oops.
Good afternoon, one and all present here. I, Priya, Assistant Professor in Department of Management Study, TIT&S Bhiwani, with the guidance of Professor B.K. Behra, Director in the same institute, presenting today's research on the topic Exploring Research Dynamics and Emerging Trends in Fiber Reinforced Composite Material, a prisma-based bibliometric analysis. Presentation. Next one is abstract of the research paper, like why we conducting this research. So this research aims to systematically examine the research dynamics, intellectual structure and emerging trends in fiber reinforced composite material. The methodology we follow the Prisma guided bibliometric framework and the R statistical package in machine learning for the analysis, and we have used a database that is Scopus based database. The key findings shows us that the publication trend is rising in this particular domain, and the composite part, the engineering journal, is the most productive and relevant journal in this particular domain. Highest used keywords are fiber reinforced plastics, reinforcement and others. When we talking about the most productive country, we found that China leads the global research output and followed by India and US. So the future researchers, policy makers can benefit from this research, and they can use the insight of this research in their upcoming decision making. Moving towards the introduction section, firstly we all know that over 50,000 plus engineering material in material worlds are there, and in which metals and alloys which are high in strength, reductivity and thermal and electronic conductivity is also high, then polymers, then ceramics, then advanced material. In composite material we have matrix type structure and reinforcement forms. In reinforcement fibers we have glass fiber, carbon and aramid. Reinforcement fibers are like carbon, aramid and glass fiber. When we are talking about the time scale, how it is developed, firstly the straw and mud bricks were there, then polywood, then hornwood, then filled concrete, then laminated iron, then Damascus, then linen, then fiber, then boron and then polymeric. And after 2000 or in year 2000, advanced structural composite era will come. So in advanced material we have nano, bio and glass optical material which are high performance polymer were also included in this. When we are talking about the trends and growth in fiber reinforced composite, we found firstly in 1970s glass was there, then carbon, then wind, and then in 2020 sustainability era will start. Now we all know sustainability and AI is very beneficial in upcoming future research, because this is bio-winds and fiber composite material which are highly usable. Now the Google trend on composite material. Like how many people all the last 5 years search about composite material on the Google, we found that in 2025 it touched 100. That means 100 indicates that the term is peak popular in this particular domain. And when we analyze on the regional basis, we found China and Ethiopia researchers maximum search about like what is composite material and how it is used in material world and what is fiber reinforced composite material. You can clearly see in the on the screen like the trend is 85% growthable from 2020 to 2026, and the peak queries like composite material, aerospace and energy. So this is the exact image from Google which show the linearly increasing trends in this particular field, and from this link you can access this image. Like in 2021 we have found only 41 average searches in this particular field, but now in 2026 it touched 100. That means this research is now the peak and most interesting and trending topic in this particular composite material domain. So when we are talking about the regional based analysis, we found China is a highly research interested in this particular field, and now we are talking about the composite material business. We found that 7,500 plus global manufacture of composite and 3,200 plus small medium enterprises in composite. 120 plus countries are actively